because it's important. Okay, and so far we were working with categories that with variables that only had a category with one level, yes or no. Okay, correctly guessed or not, exoplanet or not, I don't know. Yeah. Now, let's say we have the following data. Let's say we are interested in, is there a relationship, or what is the distribution of spectral types of stars in a globular cluster? Let's say this is our population. If we know all the spectral classes of stars in one globular cluster, 1 million stars, let's say. We know something like 80% is a G, K, or M star, 12% an F star, 0.8% an O star, and 2.9% an B star. Yeah? And we have some other that are maybe difficult to assign. And now we have a sample, and we would like to know, is there a difference between how our sample is distributed across spectral types compared to the population? Yeah. And we are doing a test. Again, our null hypothesis is saying nothing is going on. Yeah. And the test works as follows. Like always, we assume the null hypothesis is true. Under this assumption, we compute our expectation, and then we compare the expectation with the observation, or the model with the observation. So, let's say these are the population numbers, the population fractions. We know this. So that means if our sample was distributed or was representative for the population, we would expect 80.29% in our sample to be in this category, 12% to be in this category, 0.8% to be in this, and so on. Yeah? It should follow the population. And we can compute that this needs to be 2007, 302, 20, 73, and so on, given we have a sample size of 2,500. If you do this, always check that the total number adds up correctly, because here we could have some rounding errors that add up, unfortunately. Okay, so this is now the table of our expectation, and that's our observation. And now we compare the two. Again, there are some conditions for the Chi2 test. And the general form of our test statistic is, again, point estimate minus null value divided by the standard error. And in this case, if we have more than one category, it looks like this. For each of these columns in my table, I'm computing the difference between observed and expected, divide by expected, and it's take the squared difference between the model and the observations and add them up. This statistic is called Chi2. The Chi2, these statistics follows the Chi2 distribution, which looks like this. It's again a skewed distribution which depends on the degrees of freedom and becomes more and more symmetric with higher degrees of freedom. But okay. Now, this was our table. Now we compute our test statistics. So for each of these numbers, we take the difference. Yeah, 1920 minus 2007, square it and divide by 2007. Then we do it for this column. So that's here. We do it for this column here, and so on. At the end, what we get is 22.63. that's our chi-square value. And the degrees of freedom is, we have 5 columns, 1, 2, 3, 4, 5. And degrees of freedom minus 1 is then 4. So what we are looking is, what is the p-value for a chi-square of 22.6 in a chi-square distribution with 4 degrees of freedom? That looks like this here. And 22 point something is here. So that's 0. Yeah, so the area under the curve is basically very small. So this tells us that our sample deviates from the population in some way. It's not representative.